Welcome to MarineLearn, practical knowledge and training for maritime professionals. Hit the bell button, subscribe, and like the video so we keep bringing valuable content to you.
A fractured pipe or a cracked engine mount at sea can trigger catastrophic compartment flooding or fatal engine room fires. When the nearest port is hundreds of miles away, the margin for error in hot work is absolute zero. In the isolation of the open ocean, the physical integrity of a single weld directly determines whether the vessel continues to operate or suffers a total system failure. This Venn diagram illustrates shipboard repair culture. True repair is a highly disciplined procedure governed by strict environmental and metallurgical rules. Three intersecting pillars support this culture: establishing an absolute safety perimeter, mastering the physics of the equipment, and preserving exact material integrity. This mission briefing slide outlines the thesis for executing a successful repair. The operator must progress through a rigid, four-phase tactical objective matrix. Technical mastery requires an understanding of exactly how thermal direction and chemical purity dictate the safety of the entire vessel. Phase 1 begins before a single arc is struck. The immediate priority is neutralizing systemic threats to the human operator. This schematic details the armor of the welder, engineered to counter specific operational hazards. The UV filtering helmet neutralizes intense radiation to prevent arc eye, while the heavy leather cape and apron deflect extreme heat and hot slag spatters. This graphic maps multi-layered hot work threats. The inner electrical ring mandates dry rubber mats to prevent high-voltage shock. Moving outward, the chemical isolation ring requires forced exhaust ducting to prevent toxic manganese fumes from causing irreversible central nervous system damage. Perfectly isolating the environment prevents microscopic sparks or stray currents from triggering a catastrophic ship-wide failure. Phase 2 dictates the selection of the correct power source architecture from the ship's arsenal based on the specific repair requirements. This comparison matrix evaluates the available machines. On the left, the alternating current transformer offers a rugged, lower-cost option. On the right, the direct current generator provides highly controllable thermal distribution. This diagram introduces DC polarity, where exactly 66% of thermal heat concentrates at the positive pole. In straight polarity, the base metal is positive, driving heat deep into thick steel. Conversely, reverse polarity makes the electrode positive, yielding shallower penetration for thinner materials. Mastering shipboard equipment is the active manipulation of fundamental physics to dictate exactly where the steel melts. Phase 3 ensures the chemical purity and precise sizing of the consumable electrodes before striking an arc. This consumables matrix illustrates a rigid rule. The electrode's chemical composition must precisely mirror the base metal, whether mild, carbon, or stainless steel. Furthermore, the bottom scale shows that thicker mercurial requires a proportionally larger diameter electrode and higher amperage setting. This process highlights an invisible enemy: ambient marine humidity. Moisture introduces hydrogen into the weld pool, causing severe porosity and catastrophic cracking. To guarantee absolute zero moisture, the strict countermeasure mandates baking electrodes in a controlled drying oven prior to use. Once the weld is laid, the focus transitions from pre-weld chemistry to physical post-weld execution. This tactical toolkit outlines that execution. A deposited weld bead remains structurally compromised until the solidified slag is violently chipped away and the interbead deposit is brushed clean of all oxides. Respecting the metallurgy requires fighting a constant, active battle against moisture and oxidation, from the sealed storage oven to the final strike of the chipping hammer. The final phase involves selecting the precise physical application method based on the required thermal threshold of the shipboard joint. This joint methodology matrix contrasts two distinct approaches. High-heat fusion welding permanently melts heavy steel base plates together, while low-heat capillary action, or brazing, joins delicate components without melting the base metal. This comparison evaluates fusion processes. Shielded metal arc, or stick welding, provides a rugged, self-shielding arc ideal for heavy structural repairs in drafty environments. Conversely, gas tungsten arc, or TIG, offers surgical precision for sensitive, thin metals, but requires vulnerable external gas shielding. For precision metal separation, this protocol details oxyacetylene chemical cutting, a process of controlled thermal oxidation. Step 1 carries a critical warning. Standard matches must never be used due to explosive gas ignition. A specialized spark lighter is mandatory. Execution requires strict physical metrics, demanding a precise 3 mm gap from the nozzle, and waiting for the steel plate to glow a bright cherry red before engaging the oxygen lever. Flawless execution relies on choosing the precise thermal tool, a self-shielding arc, capillary filler, or oxidized flame, to manipulate the metal without destroying the surrounding systems. We apply these 4 tactical phases to a single real-world crisis, a critical high-pressure pipe failure deep in the engine room. This workflow tracks the tactical response. First, the deck is dried and exhaust is rigged. Second, DC straight polarity is selected for deep penetration. Third, baked electrodes are used to prevent moisture. Finally, the root pass is welded, chipped, and brushed pure. This recap extracts 3 core tenets. Safety is spatial, heat is directional, and moisture is catastrophic. Test your readiness. Where is heat concentrated in reverse polarity? What toxic risk requires exhaust ducting? Why use a spark lighter to ignite a torch? A weld is only as strong as the physical science and the rigorous discipline behind it. This repair culture ensures the structural integrity required for operational survival at sea.